we present a new dataset for exploring the impact of rendering method and motion quality on model performance when using multi-view synthetic data for action recognition. Our paper presents a dataset suite with 5 different types, 11 actions, 3 synchronized views, 3 environments, and 2 visual domains, synthetic and real. Human activity recognition, also known as HAR, is a task of identifying activities from video data with human motions. HAR task involves 2 major components, which are HAR model architecture and the training data. The goal of the HAR task is to classify the input video with the correct action label. In this paper, we focused on exploring the impact of training data on the success of HAR model for classifying the gestures of the input video sequence. Researchers have recently used synthetic training data to take advantage of its scalability and diversity. In this paper, we present a dataset that combines real data and synthetic data to explore the impact of using synthetic data generated using different techniques. We have 11 activities in our dataset. The first 5 are everyday gestures. The remaining 6 other actions are compound actions, which involve object handling. We collected data from 1 drone camera and 2 ground-level cameras from 24 subjects. This video is an example of what the real data looks like when synchronized. We extracted 3 test sets from real data that was used for evaluation for research questions, which will be introduced later. We also captured the video and the motion capture simultaneously in the lab. Our synthetic dataset utilizes 2 different rendering techniques and 2 different sources of motion, yielding a total of 4 different synthetic data types. Synthetic CG-MC utilizes the standard CG pipeline with motion capture, which is the most commonly used combination in computer graphics. This is an example of what it looks like at 3 different points of view. We also generated a dataset that utilizes trained models for extracting motions and for rendering called synthetic LWG-RGB. The LWG in the synthetic LWG-RGB refers to the liquid warping GAM model, which is the GAM model that is designed for motion imitation given the reference motion video and input source image for appearance transfer. From the original pipeline, we modified the background to be the CG rendered background to match the CG generated datasets. The source images were generated from the CG pipeline, where we rendered the front and back images of the avatars. This is the example of the synthetic LWG-RGB. Compared to the synthetic CG-MC data, the motion is a little more jittery and the feet are less stable. The third dataset is the synthetic LWG-MC, which is generated using a combination of the neural rendering method and the motion capture. We modified the liquid warping GAN architecture to use the motion capture-derived simple meshes and other rendering parameters to match the synthetic CG-MC. It also uses the CG rendered background images and front and back images of the avatars as source images. Therefore, this data inherits the property of the motion capture, which improves the quality of motion compared to the synthetic LWG-RGB data. This is an example video from the synthetic LWG-MC data. The final dataset is generated from the motions extracted from RGB videos combined with the standard CG pipeline. We used a post-reconstruction model from RGB videos called Vibe to reconstruct the 3D motions from 2D videos. This is an example of what the synthetic CG-RGB data looks like. With these datasets, we ran evaluation experiments to answer some research questions. The first question is, does the choice of the ML model make a significant difference in the performance? We used slow-fast MVIT and X3D for this experiment. The 3 models were each trained with real training data and evaluated with the test sets extracted from the real data. The results are the following. Slow-fast had the best performance for both the ground-level data and the aerial dataset. Based on these results, we only used slow-fast to evaluate the future experiments. They also show that the ground view data had better performance than the aerial data. This is likely due to the camera being static in the ground view data, which allows the actions to be better classified. The second research question was, does the synthetic data rendering technique affect the model performance? To answer this question, we trained the slow-fast with real synthetic CG-MC and synthetic LWG-MC and evaluated it with the same test sets extracted from the real data. The models trained on 2 synthetic datasets had the lower performance than that of the model trained on the real dataset. When we compared the 2 synthetic datasets, the performance of the model trained on synthetic CG-MC exceeded that of the model trained on synthetic LWG-MC. This suggests that using the standard CG approach as a rendering technique to generate the training data yields better results in the performance. The third research question was, does improving the motion quality of the synthetic training data improve the performance? To answer this question, we compared the performance of the models trained on all 5 datasets and evaluated with the same test sets extracted from the real data. For this experiment, we used the gesture-only data that didn't involve object handling. Additionally, the training data only includes 15 subjects. Again, the real data performed the best out of all the datasets. The results showed that using motion capture as the motion source had a minimal impact on the ground-level data, but has a more significant impact on the performance of the aerial data. This is likely because motions are captured at wider ranges of view, which makes the quality of motions more important in the drone data. The results showed that both of the CG datasets exceeded the performance of LWG counterparts, suggesting that the CG method is strictly better for the performance of the model. The fourth research question is, can we combine the synthetic training data with the limited amount of real training data to improve the performance? The idea of this is to simulate a scenario with a small amount of real data given the synthetic training data. We compare the performance of the model trained on small subsets of real data with that of the model pre-trained on the synthetic datasets and fine-tuned with these subsets of real data. The results suggest that using the synthetic CGMC for pre-training the model improves the performance. The performance was higher for 10 subject subsets. The fifth research question was, can the models trained on one camera view transfer to the novel camera view? The idea of this experiment was to evaluate the models across different views. The model trained on ground data was evaluated with the aerial test data and vice versa. The results show that the real data has the best performance for both the 5-class and the 11-class experiment. The best performance was seen for the model trained on real aerial data and tested on ground data in the 5-class experiment. We hypothesized that this is due to the wide range of views in the aerial view, allowing the model to be transferred to ground-level data more easily rather than the vice versa. In conclusion, we presented a new dataset for HAR tasks consisting of real and synthetic data at ground and aerial camera views. We used two different rendering techniques, CG rendering and neural-based, LWG rendering, and two different sources of motions, motion capture and RGB extracted motions, to generate different types of synthetic data. The rendering technique and the motion quality of the synthetic data is important for reducing the domain gap with the real-world data, and even very small amount of training data may be useful for fine-tuning to increase the performance.